So I'm pleased to introduce our speaker today. Dr. Palmer and I first met on an overlook to the Pacific Ocean in Dana Point on a terrace covered with lovely red rose leaves. This is a completely true story. We were at one of our first program meetings for a DARPA program that I was on, and apparently they got a discount if they held the reception after a wedding, and they didn't have to clean anything up. So that's where we were. It was a lovely spot, but that's when I met Dr. Palmer. He was, I believe at that time, advising the then program manager at DARPA. He then became a program manager, and I worked for him as a researcher through the grants that DARPA gives to researchers for many years. We became friends and have stayed together and continue to collaborate. You may never have heard of DARPA. I think Dr. Palmer is going to talk a little bit about DARPA. I'm going to show a video here in a second. I'll just let you know, whenever the television shows want to get to the most advanced science, secret science there is, they'll always reference DARPA. So that is apparently the definition in a television show. If they say DARPA, it's cool science. I asked Dr. Palmer here for a specific reason. What DARPA does very well is develop ideas that end up in a pitch to the administration that then get, in the end, I think DARPA has a budget of $4 billion. And most of that they give away to contractors and grants through so their process is to build the best ideas, find the best people, and then support those through financial support. And I think what they do really well is shape the ideas and set up for a pitch. And I think Dr. Palmer is going to talk a little bit about that. It's not exactly a pitch for a company like you're going to do in our final, but it's a pitch for, you should support me because my idea is so wicked cool, you couldn't not fund me. All right, I'm going to play a quick video as an introduction to DARPA, and then I'll welcome Dr. Palmer onto the stage.
Coming to DARPA is like grabbing the nose cone of a rocket and holding on for dear life.
DARPA is a place where if you don't invent the internet, you only get a B.
A DARPA program manager quite literally invents tomorrow.
We are thinking about innovation unconstrained. Where can we go?
Predict what is emerging as threats.
We're looking for the applications that seem impossible.
That passion will be saving lives 5, 10, 15 years from now.
Coming to work every day and being humbled by that.
The innovation and collaboration, it's a team effort.
We're not builders of the ultimate technology.
It's the engineers and scientists at the companies and universities that we fund that ultimately are going to bend metal and write code and deliver these capabilities to warfighters.
DARPA is not one person or one place. It's a collection of people that are excited about moving technology forward.
I'd like to welcome Dr. Palmer.
Thank you, David. I now understand the reason why our personal and professional relationship has been lined with rose petals ever since we first met. But as it said in the video, DARPA is driven by ideas. And when we talk about ideas at DARPA, we're talking about big ideas, ideas that can make a dent in the universe. As you heard the former director say, at DARPA, if you don't invent the internet, you get a B. But it's not good enough just to have the ideas. The idea is just the spark, and at DARPA we really want to build a fire. So let's talk a little bit more about that. The mission statement of DARPA is creating breakthrough technologies and capabilities for national security. And the great thing about this mission statement is it makes it absolutely clear what everyone in the building is supposed to be focusing on. But it's also broad enough that we can focus on a really wide range of ideas. So where do those ideas come from? Where do ideas come from in general? I mean, it's possible that it's a stray gamma ray hitting the right neuron. Sometimes people get ideas by looking at the intersections between different disciplines, like, for example, linguistics and computer science. That intersection is behind the large language models that are the hot technology today. And it also can be from being able to put together ideas that don't seem like they should go together. For example, a flying submarine, right? Which actually, DARPA has a program on building a flying submarine. But practically speaking, at DARPA, where these ideas come from is the program managers. And that can happen in an interview with the program manager, at a random conversation at a conference, conversations with their peers, just about anything. But the point there is that the idea can't exist by itself. We need to hire someone who has passion and energy focused on that idea. That's really kind of the air that gets the spark building up into a fire. So we hire these folks from academia, government, and industry. We bring them in on a time-limited term appointment, and that's purposeful. It drives a lot of turnover in the organization, but that way we keep a fresh stream of ideas coming in, and no one gets a chance to build a fiefdom, build their own empire at DARPA because they're gone too quickly. So when we talk to potential program managers, we don't want to hire a one-trick pony because there are just too many problems in the world, and it's really hard to predict which ideas are going to result in things like the next internet. And DARPA has found those ideas and built them into larger programs over the years. Some of the things that you might recognize are the internet, chip-scale GPS receivers that enabled us having GPS in our cell phones, Siri, which originally started out as a DARPA program called the Speech Interpretation and Recognition Interface, and mRNA vaccines. All of these ideas have origins in some defense-related purpose. For example, the internet was originally conceived for the nuclear command and control system, and they wanted to figure out a way that they could keep communicating in a network where nodes were dropping out and joining randomly. So they came up with the internet. Siri, for example, was so that commanders in the field could just talk to their devices and get information instead of just data. That spun off into a small company that almost immediately was bought by Apple. And then mRNA vaccines, we started pursuing those probably 15 or so years ago because we're sending people into areas where we don't have any idea what the germ and virus environment is out there. So we had to be able to respond quickly with vaccinations and treatments. And fortunately, we were working on that when COVID hit and had the contract vehicles in place where we could pivot very quickly and get the company to focus on COVID-19, which I think is part of the reason we can have this meeting here today. But going back to my comment about not hiring one-trick ponies, when we're interviewing a program manager, we want them to give us 3 to 5 ideas, and they are just described at a very high level. Basically, what problem are you trying to solve? What's new about the way you want to solve that problem? And who cares? And the who cares part is a really important question because there's lots of good science out there, but if you're not able to draw a line from the initial work on the basic science to some application that's going to benefit either the commercial world or the military world, then it's probably of less interest to DARPA. So we'll get program manager candidates to send these ideas to the office leadership, who will then take a look at the ideas and try to figure out if they are innovative enough, if the ideas are big enough, if they're revolutionary enough. Do they fit into our current office strategy and mission? And are we not already working on these things, which happens a surprisingly large amount of time? And there's usually one idea that will sort of pop out of the 3 to 5 that really looks interesting and looks like something that we need to start right away. So we'll get the candidate to focus on that idea and give us a little bit more developed version of what they envision the program that realizes this idea looking like. And usually Usually it's half-baked. I would say 9 times out of 10 it's half-baked. We have to turn it into something that's going to change the world, right? How do we do that? Well, fortunately, we have a framework that's been around DARPA for quite a long time. It's called the Heilmeyer Catechism, and I'm not going to brief the questions. I'll tell you a little bit about George Heilmeyer. He was the ARPA director for a couple of years in the 70s. But before that, he was actually one of the people who invented the LCD display, which started the flat panel industry moving. He also served in the government under what's now the Undersecretary of Defense for Research and Engineering. He was a captain of industry for many years. He was a member of the National Academies of Engineering and of the Defense Science Board. And while he was on the Defense Science Board, the Secretary of Defense asked the board to come up with a framework for creating programs that were actionable, impactful, and possible. And so he came up with these questions. The idea behind these questions is to have a framework to develop these ideas into something that is going to change the world. But of course, there are always hurdles, and the hurdles come in two forms. There's hurdles that come from the program managers themselves, and I kind of see program managers break into 3 different categories. They're the makers, who usually are technologists who've had experience executing complex technical problems and are pretty good at technical communications. Then there are the directors, who come from high-level management in a corporation or another organization, and they're used to coming up with expansive, big, high-level ideas and then telling somebody else to go figure out how to do them. And then there's the professor. I'm sure you're familiar with that type. They're great at coming up with the really far-out ideas, but in terms of where they're going to go, they have a very aspirational impact statement, like this is going to change the way the Army makes uniforms or something. Probably not. They also often don't really have a good idea of how to get the technology up out of the lab, what it takes to get it out of the lab and into a transition opportunity. And forgive me, but they're almost always terrible at clear, concise technical communication. So there's a lot of coaching we need to do. So there's some corresponding hurdles that come from the ideas. The maker's idea is usually really cool technology, and we're pretty sure that we can build it, that project itself is going to be successful. But it's typically incremental, and unless we can ferret out the underlying technological barrier to realizing the advantages from updating that technology, it's really not going to turn into a viable DARPA program. We've had pretty good luck doing that, and even if that's not the program that the maker PM works on when they first get there, there's lots of other vehicles like small business grants and other things that can implement that kind of a technology project. The director, one of my favorite examples was a guy who came in and said, we're going to use artificial intelligence to make secure computer chips. I mean, that would be great, right, if we could do that. That would make it much easier to design chips and they'd be safer and everything. But when you dig into how that actually works as a program, what do you mean by secure? How do you measure whether a chip's secure or not? What are the underlying technical problems that you need to solve in order to use AI to design chips? And furthermore, where are you going to get the training data? If you can't guarantee that a chip's secure to begin with, how do you train a machine learning engine to make secure chips if
your notes over here, sir.
Thank you. What, did I miss something? If you don't know whether the chips are secure to begin with, how are you going to train an AI to make secure chips? But usually we can get those into a workable program. And then the professor comes in, and those ideas are usually focused on a very particular breakthrough in technology that they want to expand and turn into something that everybody uses. Like an example I'll give later is taking a material technology and turning it into a new computer chip, a new transistor, essentially. So then comes the coaching part. I probably spend, when I was the deputy director, I probably spent 30%, 40% of my time coaching the program managers. And okay, now I'll take advantage of this real quick. So there's a couple of formulaic steps that we use to coach people. One of the most useful ones is to break the problem into steps. For example, if you've ever written a computer program, you draw a flow chart first to show where the big decisions have to be made and what actions have to be taken. If you can break a problem into steps, then you can start to identify which of the steps your idea is going to impact and how much of an impact that's going to have on the entire process. For example, you could come in with a great idea for making automated design of silicon chips, but if it only speeds up 2% of the entire process, then that's really not going to make a huge impact. So once you've broken it up into steps, which steps is your program going to change? How big an impact is that going to have on the whole process? And then we get into the dreaded thing that the program managers hate called the why spiral. Because they'll say, I want to do this. I'll say, why is that hard? They'll say, because it's never been done before. And I said, that doesn't make it hard. Why hasn't it been done before? Because nobody's been able to make this material into a computer chip. Okay, why not? Why can't we do that today? Why is that part hard? And usually after they run screaming from the room, they'll come back with some ideas and some answers on those questions, and we can drill down into something that we can actually act on. And once we've done that, we want to structure the program so that you have 2 or 3 main technical challenges, and you're attacking the really hard ones first so that you can fail quickly or learn quickly, depending on how you look at it. So what you end up with is 2 or 3 technical questions that are underpinning a hypothesis that your program is going to prove or disprove. So let me give you an example of that. The intensity squeezed photonics for integrated photonics for revolutionary detectors, or INSPIRED program, was brought to us by a program manager named Justin Cohen. And he had this great idea that you could make squeezed light, which is a quantum state of light, and you could make that in an integrated photonics chip, which is basically an optical circuit. If you've been in the physics building, you've probably seen these big, heavy 4x8 tables with a bunch of screw holes on top and a bunch of little gizmos, mirrors, lasers, filters, polarizers, and all that kind of stuff. You can do amazing things with the components on an optical bench, but you can't just stick that in an airplane or in a radio. So if we can shrink that down to a single integrated chip, one, you have more physical control of the vibration between the components, and two, it's so much smaller that you reduce the losses. You can actually potentially increase the performance of the squeezed light generator by making it integrated. And then, thank you. Actually, DARPA's all about innovation.
You could use them both.
Okay.
But it's entirely my fault. I forgot to print out before class.
That's all right. I'd have to use my glasses on the printout anyway, so it's all good. The problem was that Justin came in and said, I've got this great idea for integrated squeezed light-based detectors, and we're going to be able to make a handheld radio that has high data rate optical communications with a satellite. And he compared the performance he was going to get to the performance of the long interferometric gravity wave detector, which is miles and miles long, has a squeezed light detector in it. So there's a couple of problems with that, right? One, Okay, you want to have a high data rate handheld space radio that has an optical data link. If you actually want to do a hardware test in space, you have to start doing the paperwork to get that approved well before you know what you're actually going to test. So in the scope of a DARPA program, that's probably not going to happen. And as far as the comparison to the existing technology, that's great, but what does communications and sensing have to do with gravity waves? You're comparing something that's miles long to something that you want to build on a chip. So he immediately realized that was not going to work and shifted his pitch to a technology push-based program. Okay, first, if you can't generate the squeezed light on an integrated photonics chip and actually prove that you can do that better on a chip than you can do on an optical table, then there's no point in continuing, really, because that's the fundamental hypothesis of the program. So do that first. Then prove to me that you can take that squeezed light detector and integrate it with all the other pieces of technology that you need to make a sensor that can actually detect things below the quantum noise limit. Now that's a cool idea. Below the quantum noise limit even sounds cool. And if you could do that, then we could know things that other people couldn't know. So you put that program hypothesis together, first prove that you can make squeezed light better than the other guy, and then prove that you can integrate it into a detector that actually can do what you thought it was going to do. And now you're impacting things like material science, quantum computing, quantum communication, inertial sensing, a lot of other fields. The impact is really broad. It's going to have commercial and DoD impact. So that program started a little while ago. The example I keep using about the automated generation of silicon chips actually got started as automatic implementation of secure silicon. So one of the hardest parts about that program was that right now we design secure chips by hand. There's a lot of people who sit down and they'll design a chip, they'll test and see if they can break it, they'll redesign it, they'll test it some more. This takes literally hundreds of people and hundreds of person years and many, many dollars to do. And the Department of Defense really can't afford to put that many people on a design like that. So we do need to automate the process. But a program that automates a manual process is one of the hardest programs to define, because how do you measure how long something takes in a manual process? For example, it's probable that no two people in this room tie their shoes exactly the same way. So if I ask you to write a program that would enable a robot to tie shoes faster and more efficiently than a human, exactly where would you start? Exactly how would you measure speed and efficiency on that? That's really hard to figure out. So you have to break that. We had to break that program down into what are the underlying specific technical problems that are keeping us from designing chips automatically today. A lot of that was the data, which you'll see a lot in AI-based programs. And then how do you measure whether you're successful or not, right? If you walk into a room and tell me, I've found 100% of the security flaws in this chip, I'm not going to believe anything else you say for the rest of the day. And then another example is a program called Optimum Processing Technology Inside Memory Arrays, or Optima. And if you have any contact with DARPA at all, you'll know that the program acronym might be the most important part of the idea that you're pushing forward. So you have to come up with not only an acronym that spells a pronounceable word, but a word that actually has something to do with what you're trying to do in the program. We don't actually score the PMs on that, but they like to do it anyway. So the Optima program was a material science breakthrough that came from some university research that discovered that you could use an oxide that was already part of the advanced silicon chip fabrication process to make a one-transistor non-volatile memory, which does not exist today. So that's fantastic. There's a lot of things you can do with a one-transistor memory cell, For one thing, you can make non-volatile memory about 6 times denser than it is today. You can also use these types of non-volatile memory cells to make analog computers that can do multiply and accumulate operations, which is the mathematical basis of matrix multiplication. And matrix multiplication is behind signal processing, machine learning, communications, radar signal processing. Just about any signal processing application you can think of will use a matrix multiply. So it would be great if you could make those faster and lower power and denser. The problem with that is, sure, you can make this accelerator, and we run into the same problem with a lot of accelerator technologies. You're doing the efficient, fast calculation in the analog world, but you still have to have it surrounded by digital circuitry in order to communicate with the rest of the computing and communication infrastructure. So how much power and time is that accelerator really saving you is the question. How much overhead, digital overhead, do you need to actually use that accelerator in an efficient way? So that's just 3 program-related examples. Let's see. Another example, I'm going to just flip backwards here for a second, goes back to George. There's another way you can look at the problems. There's the more general problems that kind of fall into the Heilmeier questions. The biggest problem we see with H1, the first Heilmeier question, is that you have defined your problem statement poorly. Some people want to come in with ideas like, I want to reshore chip manufacturing to the US. I want to recreate the domestic microfabrication infrastructure. Okay, that's great. Everybody would like that, but that's a broad operational goal. It has nothing to do with the technical problem you're trying to solve. And a lot of times they will also bring in a problem statement that has goals that are not measurable. So we have to fix that right away before we can go any farther. The second question, what are the key technical challenges that prevent the problem from being solved today? A lot of times program managers will choose the technology baseline of the idea that's different from the technology that they're trying to test in their program. And then you're comparing apples to oranges, and there's really no way to tell whether you've succeeded. Also, poorly defined technical challenges, like, for example, someone could say, I want to create a heavier than air craft that can take off, fly around, and land. The technical challenges there are not taking off, flying around, and landing. They're things like lift to weight, power to drag, 3D control. So we need to refocus on the technical problems that actually underpin the idea. And the other problem that people run into on the technical problem side is that they can provide an example of a state-of-the-art technology, but they can't tell me what the fundamental limit of that technology is, so there's no way to know how much the program is advancing the technology and how far it would be possible to advance the technology. The new approach, usually we, on the first pass, we get what we like to call the flying carpet program. Everybody wants a flying carpet. How do you make a carpet fly? Or the then a miracle occurs program, where they say something like, they've defined the technical challenge well, but then they just say, and we're going to solve it, without saying why or how. On the fourth question, the mismatch between the objective and the problem statement is usually what derails you from defining what the DoD or commercial impact is going to be. And finally, the main issues we see with ideas relative to the last program is that people will come in and either try to do too much or too little in the time, with the time and money they've defined, or the objectives are unclear in the program plan, or the metrics are disconnected from the technical challenges that they've proposed. So, needless to say, we spend a whole lot of time trying to solve those challenges and get the program managers to state the idea in an actionable, impactful way. When they do, they finally get to put it up in front of what we call Tech Council, which is a group of leaders from the agency, including the DARPA director, all of the office leadership, the military liaisons, contracts, finance, legal, and they all get to weigh in on the idea. And the tricky part is that you have about 20 minutes to sell your program, your innovative multi-million-dollar, multi-year program to these people. So you have to make sure that you get the story right. The DARPA director is appointed by the Secretary of Defense and approved and confirmed by the Senate. The director is 3 steps down from the president on the government org chart, and no one at DARPA is more than 5 steps away from the president. So it's a great in that we don't have a lot of bureaucracy above us in the government, so we can act and do things that other organizations can't. So the director, since she's a political appointee, also has a limited term, probably about 4 years. Comes in from academia, industry, government, generally some previous DARPA experience, and sets the organization off in a new direction. The office leadership, on the other hand, are specialists in the area that their offices focus. So, for example, my office, it's microelectronics, photonics, manufacturing. We also have a tactical technologies office that actually builds things that fly and swim and go into space. Strategic technologies office, which does a lot of transition straight to the warfighter. And also defense sciences office, which is where a lot of the ideas that MTO, that my office, Microsystems Technology office works on, where they come from. We also have an information innovation office that is cyber and computer architectures, and biological technologies office that's working on the intersection between biology and the other fields in the offices. Interesting place to work, but that presents you with a problem that you have to describe your idea in a very clear, concise, high-level way in order to make that sale. And you're really speaking to a broad technical audience, and it can be a nerve-wracking experience. I remember the first time I went up, I felt like I had the blindfold and the cigarette standing in front of the firing squad. But the second or third time I went up, it was like, the guy with the cocktail leaning on the piano going, "Hey, how you doing?" So you get used to it after a while. But no matter how experienced you are, and no matter how well you've prepared, it's never perfect. You're always going to get questions that you didn't expect. And you're always going to get guidance on how to structure the program or how to change the idea that you really didn't see coming. So I'll reiterate that the way you put the story together is very important. You've got this idea, you want to turn it into a program. You need to start with the storyline that you're trying to pitch that describes this idea and decorate it with information, not the other way around. A lot of times when people are pitching a program or an idea, a business idea, in a field that they're not 100% familiar with, They'll go out on the web and do a search and just kind of collect all the things that look cool, throw them into a PowerPoint and try to curve fit the story to that. That does not work. There are also people who have, in PowerPoint, kind of a fear of white space. They want to cram the slide completely full of all the facts and equations and pictures that they can come up with. That also doesn't work. Like I said, decorate your story with information, not the other way around. It's important to remember the Chekhov's gun principle, which is a principle from literature where if you're writing a play and there's a gun over the mantel in Act 1, somebody's got to get shot before the play's over, right? Put in all of the information you need to support your story and none of the information that doesn't support your story. And another way to say that, I like to tell the program managers that unlike in a courtroom, in tech counsel, you have to tell the truth and you have to tell nothing but the truth, but you don't have to tell the whole truth. They don't need to know all the math behind this. They just need to know why they care and how it's going to help the warfighter or how it's going to revolutionize the commercial world. So you'll get you'll get feedback on your idea, and that feedback usually looks something like you're not being bold enough. They want you to rethink your idea and make it bigger, make it DARPA scale, make it hard, make it impactful. The second most common feedback I've seen is that you need to restructure your program so you're hitting the hardest problems first. And a lot of people don't do that. But it's kind of like the journal article review process, right? You want to take the feedback seriously, you want to address it, or else you're not going to get approved, but you really don't want to distort your idea. So it's an interesting exercise that usually takes a couple of interactions with the agency leadership to close on the final approved program. But we've had a good track record of getting that done. So, finally, you've come up with this brilliant idea. The idea has been developed through the coaching process in the organization. The idea was expressed clearly, concisely, and has passed muster in Tech Council. And you get that email that says, approved. Enjoy that for about 30 minutes because it's go, go, go at DARPA. By the time you get your program approved, you're already going to be at least a year into your term. And you want to get this one on the books, and you want to get your second program started right away. Because like I said earlier, we don't like to hire one-trick ponies. And I don't know if you've noticed this, but when a new album comes out from a new group, it's great. The songs are really cool. They've got a lifetime of experience baked into them. And then their second album comes out, and it's about playing shows and riding in a tour bus. It's kind of the same thing with DARPA program managers, right? They've been thinking about this idea that they wanted to do at DARPA for many years, sometimes the majority of their professional life. They finally have the opportunity to come to DARPA and do it, and then the question arises, what next? And that's kind of where this go, go, go thing is kind of where the fuel for the fire comes in. As Professor Ricketts said earlier, DARPA's got a budget of about $4 billion a year. And at any given time, there's maybe 150 program managers there. But there's 10 times that many people in the organization whose job is to help you do your job. So you really have no excuse for not executing. In fact, the resources at DARPA are so large and so focused on the mission that what you can do there is limited by what you actually can personally execute. Those are the resources that you have inside the building. We also have liaison officers from all the services who can connect you with pretty much anybody in any of the service labs who are interested in your technology. And when you're connected with a $4 billion research funding agency, you can call almost any researcher in almost any academic, government, or industrial lab in the country and say, hey, I want to hear about your ideas and what you're doing in your lab. And they'll say, great, come on down. What do you want for lunch? Of course, we can't accept lunch. So really, you've got this opportunity. You've got visibility and you've got connections that you've never had before. You've got this incredible organization supporting your idea, supporting you bringing your idea into reality. And then your term ends and we kick you out. So what happens to the idea at that point? Well, at that point, we bring in a new PM to run the program. And that means the idea is going to evolve further because you've got a new person looking at it who doesn't have the sunk cost bias of all the work that they put in to take that idea and develop it into a DARPA program and get that program going and execute it. So we tell the PMs who are taking over the program, you know, you're not bound to do what the former PM said with this idea. You can take it in any direction you think is appropriate. And that keeps everything fresh. As you well know, if you've ever done a research project, you learn stuff as you go along. The original intent might not make any sense halfway through the program, and if you can't re-vector and change the direction of the program, then you're going to lose out on something. So that's part of what makes DARPA what it is. So just to kind of get towards the end, again, DARPA's mission is to create breakthrough technologies and capabilities for national security. We look for the best ideas from the best and the brightest people, but it's meaningless if we can't bring those ideas to life. And fortunately, DARPA has a pretty well-established process to do that, and we have been reasonably successful with it over the years. So just to finish up here, I wanted to cover the top 10 lessons you learn at DARPA. And since at DARPA we're all about innovation, I'm going to start with number 1 instead of number 10. And that is think big, and then think bigger. Peter Drucker, the author, said that it's just as hard to do something small as it is to do something big. And why would you want to do something small? What we're interested in is ideas that actually sound impossible, but have a technical approach, a reasonable step-by-step technical approach that would allow you to achieve the goals of the program. Break roadmaps. DARPA's not interested in advancing technology along a roadmap. We're interested in making that roadmap obsolete. We're interested in coming up with the ideas that change the trends, the ideas that destroy the impossible engineering trade-offs that have limited people in the past. Ask, don't answer. One of the biggest problems that I didn't mention during the talk is that when somebody comes in after being a researcher for many years, they're used to proposing solutions to defined problems. What we're asking them to do is pose the problem, and that's much harder to do sometimes. It's a big world out there. You have an incredibly impactful, awesome idea. I can guarantee you that somebody else has already thought of it. So find out what's going on out there. What are people doing? What are people not doing? These are important things that you need to know in order to put a DARPA program together. Listen, learn, use. I'm going to tell you that ego is a barrier to innovation. You need to take advantage of all the brains that you have available. Ask people questions. Keep asking questions until you understand the problem. Make sure that you take advantage of the nearly limitless opportunity you have at DARPA to expand your knowledge. Do your homework. Make sure you completely understand the idea, the pitfalls, the problems, all the way from the inception of the idea to transition of the technology. And make sure that you can answer questions at the second or third or fourth or fifth level of detail beyond that high-level brief you're going to give to Tech Council. Because if somebody starts drilling down on the technology and you can't answer the question, you're sunk. The story sells the program. I like to tell program managers to think of Tech Council as a dinner party, not a deposition. You want to make it interesting, you want to make it engaging, you want to make it clear what your goals are. And like I said before, start with the story, decorate the story with information, not the other way around. Get it done. This is something we impress on the PMs on a regular basis. You've got a limited amount of time to work at DARPA. Execute. What you can do is limited by what you can execute. With a $4 billion budget and 10 times as many and 10 people waiting there to help you do your job, you really have no excuse. It is a term appointment, so plan your next move. And this is not a bad idea, even if you're not working at DARPA. Be observant and opportunistic. Pay attention to what's out there. Keep thinking about what might interest you. DARPA can take you anywhere, so where do you want to go? And finally, be excellent to each other. You are not ever going to do anything completely by yourself. At DARPA, you have a team of people who are going to help you out for 4 years. Your success depends on them. You should help them succeed as well. People are going to come and go, but you're building a network for life. And you have to remember the mojo curve. And with that, I'll wrap it up.
You want to have a seat over there? We're going to
Sure.
Going to ask a few hard questions here. I've got some questions from the class. Now that you'll give me back my iPad, I can read those questions. I want to borrow your slides because I wanted to go back to start out here. First off, I know how big things are, but how big are programs at DARPA?
Dollar-wise, time-wise?
Yeah.
They range anywhere from $30 million to $850 million.
Okay, so $850 million would be a rather big investment.
Yeah, they're usually executed over somewhere between 3 and 5 years as well.
Okay, great. So that's sort of the scale. And now one of the things at DARPA is the people who help you out, not that they get you coffee, but if you ask for coffee, there usually would be 2 PhDs who went to a very good school who will bring you coffee and talk about your needs. So sort of the hierarchy is you've got the director, and you've got the directors of the different areas, then there's the program managers, and then that's kind of it for DARPA for actual employees. Isn't that correct?
Yes.
And everybody else is a contractor.
Well, we have government employees in finance and legal and contracting.
But it's sort of in the, if you will, the crux of the creation.
In the technical areas, right. Yeah, it's all term appointments.
And so each program manager will have several, possibly PhDs, just there to help out with slides, research. So I think one of the things that surprised me about DARPA was it really is not resource constrained. You have all the money you need. You have all the support you can get. And it's a little bit nerve-wracking, maybe a little bit.
just remember, you have to talk people out of that money, right? It's not just floating around out there.
No, I agree.
But you mentioned the support contractors. Yeah, each PM has typically master's or PhD level scientists. They also have someone who does the interfacing with contracts and the bookkeeping on their budget and so forth, make sure people are invoicing and so forth. So it really is an amazing support network. I've got a story about that. Actually, I worked for the Army for many years, and Army Research Office, and they allowed us to have business cards, but we had to print them using their template, but we had to pay to get them printed ourselves. Okay. So I get a job at DARPA, and I show up work day one, and there's a pile of business cards on my desk. And I was like, this is awesome. They were even good paper, you know. So when you're at DARPA, there's a lot of people who want to meet with you right away. So I went through that stack of business cards pretty quick. And I was about to go to a conference. I was thinking, oh, gosh, I'm going to go to this conference, and I'm not going to have any cards. Well, I'll just put in an order, so I'll have them when I get back. So I called down to Visual Media Services, and I said, hey, this is Dev Palmer. I need some more business cards. They said, how many do you need? 250? I was like, sure. And they said, we'll have them to you in an hour. Is that okay? And that's just emblematic of how DARPA works, right? People are there to support your job, to support the mission. It's unlike any other government agency that I know of. In fact, it's unlike any other organization I know of. It's just a great place to work.
So I wanted to touch on two pieces. One was there's this sort of statement, everything has to be DARPA hard. So what is DARPA hard?
Well, right near the end, I mentioned that the programs have to sound impossible, right? You want to stretch people. You want to induce new ideas from the performer community. We don't actually do any of the work ourselves, so we can ask for goals that are as outrageous as we can justify. So the ultimate goal of the program is going to be impossible. But you still have to be able to make a reasonable technical argument that it's achievable. That argument can include new innovations that have to occur, but there has to be some realistic basis that those miracles actually will occur, or else the program's not going to happen, right? So you can roughly equate DARPA hard and impossible, I guess, if you want.
So to give you all a concrete answer to that, the program that we were on, we were making something, and first phase was 50% efficient, second phase was like 75% efficient. We were thrilled when we set a world record at 30% efficiency on that program. So that is sort of where they go. The other piece is, in DARPA lore, is if you're not spending money, you're not doing work. And I'll just couch this. This is not wasting money, but this is, if there's any way to do it faster and get it done better, you have the resources to do that.
Yeah, think about it this way. A $4 billion a year budget means that if the agency director works a 60-hour week, takes 2 weeks of vacation a year, and does nothing but sign checks, they have to sign checks at $1.25 million an hour in order to obligate that budget. So anytime you have an idea, you stick your tin cup out into the stream of money, and if you can convince the agency director to approve it, you can do it.
Great. So there's a couple things in your presentation I thought might be applicable to our final project and sort of innovation in general, so I wanted to maybe ask some questions on that. I like your top 10. I want to go to the number 1. Think big, now think bigger, now think even bigger. What are some really big, impossible ideas that you've seen?
That's there's a lot of them that I've seen. I mean,
what would be the most interesting to share that you can talk about?
Well, I've been watching a lot of television lately, and I think it's fair game to answer a different question from the one that you asked.
Sure.
Okay.
You're the professor for the day.
I think I think what interests me most, the wild ideas that interest me most are the ones that are material science related. Rather than giving you a specific example, one of the reasons we've been able to keep semiconductors moving forward over the many years is that we are exploring the periodic table and using elements that we didn't think we could use before. Every element in the universe has some unique property, like some are magnetic, some make good transistors, some make good capacitors. It's a mix and match. And it seems to me like there's got to be some combination of elements that we haven't thought of that is going to take us into that next level of semiconductors that are efficient, that are fast, that just increase performance generally. So that's like tightly related to my field. There's also some really interesting things coming out of the intersection between electronics and biology. I mean, I think people have heard of the prosthetics that DARPA has been working on that actually have a two-way connection to your brain. You can just think and make the prosthetic move, but now they also have pressure sensors on the fingertips that can send touch back to the brain. That's amazing. But that's just the start, right? I mean, how far are we from the Matrix, right? How long is it going to take for them to give me a little SD card slot behind my ear so I can actually remember stuff for more than a week?
So how far and crazy is too crazy? How do you separate big and bold from just darn right crazy?
I think it's really in the justification of the possible technical approaches. It's got to be enough of a stretch that you can't do it with the technology that we have today. But this is where understanding the fundamental limits is pretty important, because if you're proposing something that actually violates the laws of physics or electrodynamics or chemistry, it's really hard to justify. But on the other hand, people have come up with new ideas of how to interpret the laws that we've considered immutable just by dropping the assumptions that have been made in the research that's happened to date.
Right.
So.
Okay. One of the interesting things I heard you say was it can't be possible now.
Yes.
Which I think is an interesting perspective. I just want to go back and touch on the Heilmeier criteria. By the way, he had an amazing slide deck that he had to submit, I'm sure, to your public relations office, and this is all that he was allowed to show at the end of that. So, I look at this, and first off, you said in the directorate that you work in, you don't always do these 5. So is there a MTO different set than you use these 5, or how do you adapt them?
Well, actually, the official DARPA formulation of the Heilmeier Catechism right now has 9 questions.
Okay.
But you could argue that at least a few of the questions are duplicative or can be absorbed into these 5. So we've been using these 5 for MTO just to make it a little bit more compact. These 5 questions are great when you're formulating a DARPA program. Okay, that's really what they were built to do. Mm-hmm. They're also very useful when all 5 of them are useful when you're writing a proposal in response to a DARPA program, because it kind of gets you in the same mindset as the program manager who formulated the proposal. But if you're talking about monitoring ongoing research, then it's really only the first 3 pretty much that you need. And the new approach and how is it different from today's technology needs to be updated every time you're reviewing your program, because we don't live in a vacuum. Technology is changing incredibly fast these days. So you can actually have a program that was a great idea at the beginning and is totally moot at the end, depending on how the environment's changed.
Right. So for all of you out there who are thinking, what do I need to do for my final project for the pitch? I know you're not doing a DARPA pitch, but it should follow these 5. This is exactly the way to develop your commercial idea. Because in the end, it's about, the first one is, where's the value proposition? You're trying to understand what are the barriers to getting it done today. Then you're looking at why you have a new idea. One of the things to address in your pitch for a new company is, why is your idea unique? And I just want to let you, I went to a pitch just a couple of days ago, and they were pitching something, and I said, well, hey, why is your idea unique? Everyone else is doing it a different way. It's great. Why is your idea better? Because it's not what everyone else is doing. I said, perhaps everybody's doing it that way for a reason. Nope, I'm different. But they weren't able to get beyond that piece. But I think one of the things when you talk about pitching your companies is, what is your unique approach or thought? Looking at the impact, you guys are probably not pitching the DoD, but one of the things is, if I went into the DARPA director and pitched a $10 million program, would they take me serious?
I'm sorry, but the only answer I can give you is it depends, right? Depends on what you're asking to do.
Right.
If you're asking to get to a proof of concept on a crazy new idea, then probably yes. If you're asking to do something that's not particularly ambitious, then not only will they say no, but they probably won't allow you on their calendar anymore.
No, I guess what I'm trying to get at is there's sort of a minimum expectation of the value proposition you're trying to address.
Yes. Yes.
If it's not a big, bold problem, then let's not do it.
Yeah, but we have a little bit of a different way to measure return on investment. At DARPA, we're not looking for a 10x return on the venture capital money that we put in. We're looking for a 10x improvement in capabilities. And 10x is kind of the minimum you get at DARPA. It's usually better if it's many orders of magnitude. But again, you have to be able to justify why you think you can do that.
Right. But it's a big, you're only looking at the big ideas. Small ideas are not ones that you want to pitch and invest in.
Another way to rephrase the fourth question, I think that's relevant to commercial, is who cares, right? Who's going to buy it? Who's interested, and why?
So we had a couple questions from class. One of them, several of the questions revolved around the role of AI in developing new technology. And there's several different questions. One could frame it as the role of AI in the development of new technology, and then one could talk about the development of new AI. Mm-hmm. And I just wondered if you had, they were the questions they submitted. I don't know if you can talk about anything on that or had any comments.
Yeah. Oddly enough, most of the stuff that DARPA does is unclassified. We get this reputation as being a big secretive organization, and if you want to see how secretive we are, you can check our LinkedIn feed, our Twitter feed, our YouTube channel, or our public webpage. But in terms of AI, on our public webpage, you'll find that we actually just launched a new program on what is the future of AI, basically. DARPA relies on the great minds out in the research community to come up with those ideas. In terms of AI as part of technology and for developing technology in the past, people have used genetic algorithms to do electronic design for a long time. The real breakthrough that created the AI we have today was actually that computing and memory caught up with the data storage and computational needs for training and inference that is done in the machine learning. If you come in and say that, I hate to keep beating on that chip design program, but if you walk in and you say, we're going to make this better with AI fairy dust, that's not a good program pitch, right? What exactly are you doing with the AI? Is it generalized black box machine learning, which really is basically just a multi-dimensional curve fit? Or are you guiding the AI with any fundamental physical principles to simplify the training and inference? And probably most importantly, where are you going to get the training data, and why do you believe that data?
So I think that's important. This is the first time I've heard of AI fairy dust. But we have waves, particularly in this class and final projects, where a magical technology will be pitched as the solution to everything. About 8 years ago, it was all in 3D modeling and scanning with your phone. And now you can. You can try on clothes, on apps on your phone, and it became a reality that was there. Great. Last question for you is, we've got a lot of bright young people here. If you can remember, I don't know, 80, 90 years ago when you were 20. Sorry, just had to get that one in there. What do you wish somebody had said to you when you were an undergrad that would have made a difference in your career?
You're not going to make a living as a musician.
What do you play?
I played guitar back then, but I was interested in science and technology back then, but I think I just didn't understand the art of the possible. I didn't know that there was a DARPA out there. I didn't understand how research got done or how research got funded. Maybe a little bit of an explanation of how that happened and how I could get in on it would have been helpful. I caught up eventually, but...
Yeah, no, I think the art of the possible is something that, even for me, with aspirational research goals, you go and talk to DARPA, and it's an order of magnitude bigger in the thought process there. I want to thank everyone, and I want to thank Dr. Palmer for his time here. Thank you very much.
Thank you for inviting me.